Before leaving last time, we drew this electronic configuration for calcium. Before that, we did for argon as well. This is for argon that we did, right? Let me clean this one. So let me write it well for you. So yes, and we have argon. Then we do the electronic configuration. This is how it looks like, and this is for calcium. I want to. So it means that from here to here was for argon. Remember, we see the structure. Argon is from 1s2 fully filled up to 3p6, right? So this one can also be written as argon is how do you call it? A sample that we use to capture all this. So if you write argon 18 like this, it means that we assume that it has been filled in this way up to this point. This is just a shortcut, right? To just represent argon in this way. So argon is usually a substance that is fully filled and stable. So we are considering that stable as the starting point of the next one. So I can also write this calcium as from 18 for argon. Now I will now fill the rest, which is 4s2. 4s2. So if I write this one alone like this one alone like this, it just means calcium. It's the same calcium, but then I'm able to capture all these things together into argon, because argon will be the one that is fully filled like this. Then I just add any extra one. So before you move to the 4s to the 3d and all that, right, in the list, right? So if you move from here to here, right? No, not the D is not part. The D is not part. The D is not part. So if you move from here to here, before you move to the 4s and 3d stuff where the switching occurs, you can represent all this by just simply doing argon. This is just a simple shortcut, but then I'm just going to use that to explain to you. But then when they ask you in examination, make sure you break it down fully, right? So we assume that when we are doing something like, we assume that you know how to fill from here to here before we proceed. Okay, so now there's something about the stability rule, right, around 4s2 and all that. There are some elements that don't actually follow Aufbau's rule when it comes to the stability. They include copper. So copper Cu24, right? This one is so in filling this, I'm going to assume again, right? For argon is 18. So meaning that I need to fill the 4s and then the 3d, right? So if 18 electrons have been filled already from here, then it will be left with 6 electrons, right? So for the 6 electrons, what happens is that 4s is an s, right? And the s can take a maximum of 2 electrons. So 2 electrons will enter here, right? So it will now be left with 4 minus 2, which is equal to 4. So the 4 electrons will now enter the d. Remember, d is a degenerate orbitals with 5 suborbitals. 1, 2, 3. 1, 2, 3, 4, 5. So this is a 3d orbital, right? Okay, so but we are having 4. So that 4, we are going to fill in parallel first. 1, 2, 3, 4, right? 4. This is 4. Okay, and the stability rule was telling us that in filling degenerate orbitals, right? No, it's saying that half of fully filled orbitals are stable. Half of fully filled orbitals are stable. So what is going to happen is that you see the 3D, the orbitals are will be more um inclined to be stable. Everybody would like to be stable, so they'll be more inclined to becoming stable. So what happened is that the 4s and the 3D between them, they are close. These guys are very close. They are very close on the shell. So yeah, in the atom, they are very close. So what happened is that 1, 2, 3, 4, 5, right? There's a one empty one. This 3D is supposed to take a maximum of 10. For it to be stable, it needs to be what? Half of fully. So if half of electrons are filling this orbital, meaning that we can take a 5 electrons, right? 5 can fill it. Are we okay? Now, if 5 failed it, then this orbital will be stable. If 10 failed it, then it will be stable because the stability rule says it should be half of fully filled orbitals are stable. But what we have right now is that in the 3D we have one, two, three, four. It's not, and this one is empty for now, right? But then don't you think that if we can have an extra one here, let me use another color. If you can have an extra one here, then one, two, three, four, five, it will make these two to have five electrons, and that will be stable, right? Okay. So and then this 4s that is close to the 3D, if we are able to remove one from here and pass it to this guy, if we pass it to this guy will become half filled, right? Half filled, which will be stable. And then if you remove one from here, right, this new orbital would just become something like one. And it's an s orbital, and s orbital will be stable if it has one or if it has two electrons, because half of fully filled orbital are stable. So this guy will still maintain stability, and this one will also maintain stability if this guy is able to pass one of his electrons to this guy. That's why when it comes to the copper, right, because of stability overrides the of Bohr's rule, because of Bohr's rule says that orbitals of lower energy should be fully filled first, but of Bohr's rule says no. Sometimes there should be room for like some adjustments in order to accommodate for stability. So what actually will then happen is, let me use another color, that this electron will pass from here into this one. So it will now have one here, and this guy will disappear, right? This guy will disappear. If it disappears, the entire electron will now become something like this now. So let me clean this and write it in the middle here. So this 4s will become 4s1, and then this will become 3d5 because of the electron that you have been able to pass. So when it comes to this, right, copper, there's this particular um exception that happens around that guy, right? So there's a passing of electron from here to here. So this guy is still stable, and this one also attain its stability. So that's very fine. So because of the stability, half of fully filled orbitals are stable. So if you do that, this orbital is having 5 electrons, right, which is half of the maximum 10 that is supposed to take. This one is also having one, and one is half of two, because s orbital should take a maximum of two, and d orbital is supposed to a maximum of 10. So they are able to have five, half, half. So half of fully orbitals are stable. So they all satisfy the stability. It's better to be stable than just be following rules, right? So that's how this one also failed, right? It doesn't just work with uh, carbon. It doesn't come with copper, sorry. So let's assume that we get to a point where this is not copper. This is not supposed to be copper. I wanted to mean this one 24 is for chromium. Chromium, Cr, chromium. Chromium is, and the next one is copper. The next one is copper. Let me clean this side. The next one is going to be copper, right? So copper is 29 basically. So if you are feeling that we are going to have argon, we assume that you fill up to argon 18, right? So you now be left with 4s and the 3d. So see, the 4s, the if you remove 18, right, it's going to be left with about 11 electrons to fill, right? So let's not do the normal stuff. This guy will take 1 1, and this guy will take 1 2 3 4, right? 1 2 3 4 5. Okay, so yeah, 11, and this one takes 2. It will be left with 9, right? So 9 is supposed to enter this guy. So we have parallel filling first: 3 4 5 6 7 8 9. Okay, this one is also close to becoming fully stable, because this one is supposed to take a maximum of 10. The 3D is supposed to take a maximum of 10, but right now it's 9. So stability rule says that half of fully filled orbitals are stable. This one is 9. So he's left with only one electron to become fully filled, right? So it's close to becoming stable. And if this 4s is able to give one electron to this guy again, then this one will become fully stable, and this guy will be half filled and still maintaining stability as well, right? So if that thing happens, that borrowing thing will happen again, then one electron from here will go and be passed and then pair up with this one to make this guy fully stable to become 10 electrons in the D, and the 4s will now maintain 1. So 3D10. This is the full stability. This is how stability comes in, because half of fully filled orbitals are stable. Because of that stability, this transfer of electron happens to make sure that is okay. So when it comes to copper and chromium, be remember that they are very close. The 3D orbitals is very close to becoming half filled when it is chromium, or fully filled when it become copper. When it is almost close, then the 4s can donate one electron to this one and then become fully stable. So this guy is stable because it's half filled, and this one is stable as well because it's fully filled. That's how stability overrides of both rules in this particular case. These are the exceptions that you need to know and then master. Yeah. So let's see what happens in the next session.